On September 13, 2023, astronomer Niku Madhusudan at the University of Cambridge released data from the James Webb Space Telescope that should not have been possible to collect. His team had analyzed the atmosphere of an exoplanet called K2-18b, a world located 120 light-years from Earth, 8.6 times more massive than our planet, orbiting a red dwarf star in the constellation Leo. And in that atmosphere, Webb's infrared spectrometer detected something that violates every model of planetary chemistry we have built: methane, carbon dioxide, and dimethyl sulfide. Methane and carbon dioxide are common. They exist on Venus, Mars, Titan, and the atmospheres of gas giants throughout our solar system. But dimethyl sulfide is different. On Earth, it is only produced by living organisms, specifically marine phytoplankton. Microscopic algae that release the molecule as a metabolic byproduct when they break down organic sulfur compounds in seawater. No known geological process creates dimethyl sulfide in planetary atmospheres. No volcanism, no photochemistry, no lightning or mineral weathering. It is a biological signature, a waste product of life. And Webb detected it in the atmosphere of an alien world. But the detection was not definitive. It was tentative. The signal was faint, buried at the edge of instrumental sensitivity, requiring further observations to confirm, which means we are not announcing the discovery of extraterrestrial life. We are announcing that we have found a molecule that, if confirmed, has only one known explanation. And the most disturbing part is not the molecule itself. It is where it was found. Because K2-18b is not an Earth-like planet. It is a Hycean world, a hypothetical class of planet covered entirely by a global ocean, hundreds of kilometers, deep beneath a thick hydrogen-rich atmosphere where the surface pressure is so extreme that water transitions into exotic high-pressure ice phases. Life on such a world would not resemble anything on Earth. It would exist in an environment we have never observed. It would be producing chemistry we are only now learning to detect. K2-18b is not a mystery because we do not know it exists. The planet was discovered in 2015 by NASA's Kepler Space Telescope, which detected periodic dimming of its host star as the planet transited across the stellar disk. The transits occurred every 33 days, indicating an orbital period that placed K2-18b squarely in the habitable zone, the region where temperatures allow liquid water to exist. The mystery is what kind of planet it is. K2-18b has a radius 2.6 times larger than Earth and a mass 8.6 times greater. That density is too low to be a rocky world like Earth or Venus, but it is too high to be a gas giant like Neptune. It occupies an intermediate category called a sub-Neptune, a class of planet that does not exist in our solar system, but appears to be the most common type of world in the galaxy. Sub-Neptunes are enigmatic. We do not know if they have solid surfaces, or if they are entirely gaseous, or if they are covered by deep oceans beneath thick atmospheres. For years, astronomers assumed that most sub-Neptunes were mini gas giants, scaled-down versions of Neptune with hydrogen-helium atmospheres and no potential for habitability. But in 2021, astronomer Niku Madhusudan proposed a different possibility. He suggested that a subset of sub-Neptunes might be Hycean worlds, planets with global oceans and hydrogen-rich atmospheres where the conditions for life could exist despite the alien environment. The oceans would be hot, between 0 and 200 degrees Celsius, depending on depth and atmospheric pressure. But they would be liquid. And chemistry favors liquid water as a solvent for biochemistry. Madhusudan calculated that Hycean worlds could be far more common than Earth-like planets, easier to detect atmospherically, and potentially more conducive to life because they're thick. Atmospheres would protect the surface from stellar radiation and cosmic rays, while maintaining stable temperatures over billions of years. K2-18b was the ideal test case. It had the right mass, the right radius, and the right orbital distance to potentially be a Hycean world. And in 2019, astronomers using the Hubble Space Telescope detected water vapor in its atmosphere, the first confirmed detection of water on a potentially habitable exoplanet. But Hubble could not determine whether the water was in a thin atmospheric layer or part of a global ocean. For that, astronomers needed Webb. The observation began in February 2023, when the James Webb Space Telescope pointed its near-infrared spectrograph at K2-18b and waited for the planet to transit its host star. During the transit, starlight filtered through the planet's atmosphere, and molecules in the atmosphere absorbed specific wavelengths, creating a spectroscopic fingerprint that revealed the atmospheric composition. Webb's sensitivity allowed it to detect absorption features far fainter than Hubble could. And the data, when processed, revealed not just water vapor, but a complex atmospheric chemistry. Astronomer Niku Madhusudan led the analysis team, which included researchers from the University of Cambridge, NASA's Goddard Space Flight Center, and the European Space Agency. They identified absorption features corresponding to methane, carbon dioxide, and water vapor, all consistent with a hydrogen-rich atmosphere. But the relative abundances were unexpected. Methane was depleted. Carbon dioxide was enhanced. This was the opposite of what equilibrium chemistry predicts. Methane should be abundant because hydrogen and carbon naturally combine to form CH4 at the temperatures and pressures expected on K2-18b. Carbon dioxide, which requires oxygen, should be scarce. But the data showed the reverse, which suggested that something was consuming methane and producing carbon dioxide, a chemical process that operated out of equilibrium. On Earth, this process is called photosynthesis. Plants and phytoplankton consume carbon dioxide and release oxygen. Methane is consumed by methane-oxidizing bacteria, which break down CH4 and produce CO2 as a waste product. These biological processes create atmospheric compositions that deviate from chemical equilibrium. K2-18b's atmosphere deviated in the same way. And then, Madhusudan's team found the dimethyl sulfide signature, a faint absorption feature at 2.7 microns, exactly where DMs absorbs infrared radiation. The signal was weak, only a few parts per million in concentration, barely above the noise threshold. But it was there. And there is no known abiotic process that produces dimethyl sulfide in atmospheres. The team ran models to determine if photochemistry, lightning, or volcanism could generate DMs. None of them worked. Sulfur exists on rocky planets, released by volcanic outgassing as sulfur dioxide or hydrogen sulfide. But converting those molecules into dimethyl sulfide requires organic chemistry. The same reactions that occur in Earth's oceans when phytoplankton metabolize sulfur-containing amino acids. If the detection is real, it is a biosignature. But the signal required confirmation. A single detection, no matter how compelling, is not proof. Webb would need to observe K2-18b again, during multiple transits, to verify that the dimethyl sulfide absorption feature is repeatable and not an instrumental artifact or contamination from some unknown source. Why does a planet 120 light-years away have chemistry that only life produces on Earth? Till now, this looked like a tentative biosignature, a molecule that might indicate life, waiting for confirmation from follow-up observations. But it was not waiting for confirmation, because in October 2023, astronomer Subhajit Sarkar at Cardiff University published a reanalysis of the Webb data using a different atmospheric retrieval algorithm. Atmospheric retrieval is the process of inverting spectroscopic observations to determine the composition and structure of an exoplanet's atmosphere. Different algorithms make different assumptions about cloud coverage, temperature gradients, and molecular abundances. Sarkar's algorithm found no dimethyl sulfide. Instead, it attributed the 2.7 micron absorption feature to methane, which also absorbs at nearby wavelengths. His analysis suggested that Madhusudan's detection was a false positive, an artifact of model assumptions rather than a real atmospheric component. The discovery appeared to collapse, but Madhusudan responded with his own reanalysis. He demonstrated that Sarkar's model underfitted the data. It could not explain all the observed absorption features without including dimethyl sulfide. The methane-only model left residuals, unexplained dips in the spectrum that matched the expected signature of DMs. The debate became technical. Disagreement over statistical methods, prior assumptions, and the treatment of instrumental noise. But underneath the technical arguments was a deeper question. Why were scientists so eager to explain away the dimethyl sulfide detection? This is the hidden barrier, not the difficulty of detecting biosignatures, the reluctance to accept them. Because accepting dimethyl sulfide on K2-18b means accepting that life might exist on a world fundamentally unlike Earth, a planet with no solid surface, an ocean so deep that it transitions into high-pressure ice at the bottom, an atmosphere so thick that sunlight barely penetrates, And yet, somehow, life emerged. Life adapted. Life produced chemistry detectable across 120 light-years of space. And if life can exist on Hycean worlds, then the galaxy is far more habitable than we thought. Because Hycean planets are common, Webb has already identified dozens of candidates. They orbit red dwarf stars, the most numerous type of star in the galaxy, which means they are everywhere. Scattered throughout the Milky Way, potentially hosting biospheres we would never have thought to search for. But the biosignature interpretation had another problem. It required that life on K2-18b was not just present, but abundant. Because for dimethyl sulfide to accumulate in the atmosphere at detectable concentrations, billions of tons of the molecule must be produced every year. On Earth, phytoplankton release approximately 1 million tons of DMs annually. For K2-18b to produce a detectable signal, its biosphere would need to be far more productive. Why would life on a Hycean world be so prolific? In December 2023, astrobiologist Sarah Seeger at MIT published a study modeling the potential biochemistry of Hycean worlds. She proposed that life in a global ocean beneath a hydrogen atmosphere might rely on hydrogen itself as an energy source, using chemosynthesis rather than photosynthesis as the primary metabolic pathway. Chemosynthetic organisms on Earth, like those living near hydrothermal vents on the ocean floor, derive energy from chemical reactions rather than sunlight. They oxidize hydrogen sulfide, methane, or molecular hydrogen, producing organic compounds and releasing waste gases. If Hycean life operates this way, it could thrive in the deep ocean, where sunlight never reaches. Sustained by the hydrogen-rich atmosphere above, Seeger's models predicted that chemosynthetic life on K2-18b could produce dimethyl sulfide at rates far higher than Earth's phytoplankton, because the ocean would be in direct contact with a massive reservoir of hydrogen in the atmosphere, creating a continuous energy supply. The biosphere would not be limited by photosynthesis. It would be limited only by the availability of nutrients and the rate at which chemical disequilibrium could be maintained. But the model required one critical assumption. It required that K2-18b actually has an ocean. We do not know if it does. In March 2024, astronomer Boudjane Benick at the University of Montreal led a team that used Webb's mid-infrared instrument to observe K2-18b at longer wavelengths, where thermal emission from the planet itself could be detected. Unlike transmission spectroscopy, which measures starlight passing through the atmosphere during a transit, thermal emission spectroscopy measures the heat radiated by the planet, providing information about temperature structure and the presence of clouds or hazes. Benicky's observations revealed that K2-18b's atmosphere is not uniform. There is a temperature inversion, a layer in the upper atmosphere where temperature increases with altitude rather than decreasing. On Earth, temperature inversions are caused by ozone, which absorbs ultraviolet light and heats the stratosphere. But K2-18b's inversion was far stronger, suggesting the presence of a photochemical haze, a layer of organic molecules formed when methane is broken apart by stellar ultraviolet radiation. This was critical evidence, because photochemical hazes only form in hydrogen-rich atmospheres with significant methane concentrations, and their presence confirmed that K2-18b is not a rocky planet with a thin atmosphere. It is a world with a thick, extended atmosphere dominated by hydrogen, exactly what the Hycean hypothesis predicts. But the thermal emission data also revealed something unexpected. The planet's day side was cooler than models predicted. Most exoplanets are hottest on the side facing their star, where stellar radiation is most intense. But K2-18b's day side was only slightly warmer than the night side, suggesting that heat was being redistributed efficiently across the entire planet. On gas giants, heat redistribution occurs through atmospheric circulation. It's winds that transport thermal energy from day to night, but K2-18b is smaller with lower wind speeds. The efficient heat redistribution suggested something else was at work, something with high thermal inertia, an ocean. Astronomer Eliza Kempton at the University of Maryland analyzed the heat redistribution, found that a global ocean hundreds of kilometers deep, with surface temperatures around 100 degrees Celsius, could explain the observations. Water has enormous heat capacity, absorbs thermal energy during the day, and releases it at night, smoothing out temperature variations far more effectively than atmospheric circulation alone. This was the proof that K2-18b is a Hycean world, It's not definitive, but consistent. A planet with a hydrogen atmosphere, a photochemical haze, and a global ocean maintaining thermal equilibrium across its surface. And if K2-18b has an ocean, then the dimethyl sulfide detection becomes far more plausible, because DMs on Earth is produced in seawater, not in the atmosphere. Phytoplankton release it into the ocean, where it dissolves and eventually outgasses into the air. If K2-18b has a similar process, then its ocean could be a biosphere, teeming with microbial life producing waste gases that accumulate in the atmosphere. But the final confirmation requires one more observation. Webb needs to detect dimethyl sulfide again during a different transit, using a different instrument to rule out the possibility that the original detection was a statistical fluctuation or a systematic error. That observation is scheduled for 2025. On September 13, 2023, Niku Madhusudan announced the detection of dimethyl sulfide in the atmosphere of K2-18b. He did not know he might be announcing the first chemical evidence of life beyond Earth. He thought he was reporting a tentative detection, a molecule that would eventually be confirmed or ruled out by follow-up observations. 18 months later, the detection remains unconfirmed, not because the signal was wrong, but because confirming biosignatures requires extraordinary caution. A single detection is not enough. A single molecule is not enough. We need multiple observations, multiple molecules, multiple independent confirmations, before we can claim that we have found life on another world. But the deeper question is not whether K2-18b hosts life. It is what it means if it does. Because K2-18b is not an Earth analog, is not a rocky planet with continents and shallow oceans and an oxygen-rich atmosphere. It is an alien world, a Hycean planet, a class of environment that does not exist in our solar system, and that we never thought to consider habitable until a few years ago. And if life can exist on Hycean worlds, then the number of potentially habitable planets in the galaxy is not millions, it is billions. Because sub-Neptunes are the most common type of exoplanet. They outnumber Earth-sized worlds by factors of 10 or more. And many of them orbit in habitable zones where liquid water can exist, which means we have been searching for life in the wrong places. We have been looking for Earth twins, rocky planets with thin atmospheres and temperate climates. But the galaxy might be filled with Hycean worlds, ocean planets beneath hydrogen skies, hosting biospheres that operate on entirely different principles than life on Earth. And once you realize that life does not require an Earth-like planet, that biology can adapt to environments we assumed were hostile, you start to understand how narrow our conception of habitability has been. How many exoplanets have we observed and dismissed as uninhabitable because they did not look like Earth? How many atmospheres have we scanned without searching for the right molecules because we did not know what biosignatures to expect? And once you accept that K2-18b might host life, that a world 120 light-years away might have an ocean filled with organisms producing chemistry we can detect from across interstellar space, you start to realize that the search for extraterrestrial life is not a distant dream. It is happening now, with instruments we have already built, on worlds we have already found. Subscribe to Universe Uncovered, because the universe is not empty, it is chemical. In chemistry, when given liquid water and energy, does not stay inert, it becomes biology. And we are only now learning to recognize it.